this mod of A type notation. Right. So this is what I needed. Now what I need here is the notion of what it means to add two sets in the sense of Minkowski, right? And how do we define this? Well, let's think about it graphically first. So I'm trying here to define some notion of addition between sets, right? Well, the natural way to do it is the following. If you're given A and B as subsets of Rn, then you define A plus B as the set of all pairwise sums of elements of A and B. So A plus B where small a is in big A and small b is in big B. Now the way to think of this object geometrically is that, let's say, I don't know, A is perhaps a triangle and B is perhaps a circle. So maybe this is A and this is B. So what you're doing is you're taking each point of A and you kind of paste a circle at that point. You paste a copy of B at that point. So for example, in this diagram of A, I have labeled certain points and now I sort of paste B at each point. So I paste B. There's a copy of B at each point. And put together, everything put together will then form A plus B. So the way of thinking about A plus B is precisely that kind of geometric pasting notion, if you like. Right. And analogous to addition, we have the notion of scaling, right? So how do you scale a set? Well, you multiply every element by some particular quantity. So given a subset of Rn and t greater than equal to 0, you can define the set C small a as just C big A as C small a for A in big A. So the way again of thinking about this is that literally you're just zooming in or zooming out of a particular set. So for example, if this is B, then you would expect half B to be something half the size and 2B to be something twice the size, for example. So that's the natural way of thinking about scaling, right? And finally, a notation that will be endemic to this talk is the notation of a closed ball. So under the usual Euclidean distance, which we will not be moving away from in this talk, you define the set of all y such that the distance between x and y is less than equal to r, and that's denoted b of x comma r, the closed ball of radius r around x, where x is in Rn and r can be possibly 0 as well, in which case it would just be a single point. Now there are some properties there are some ways in which addition and scaling and so on interact. I'll just mention these properties without proving them. Properties. You can verify these. These are all fairly straightforward to verify from the definition. Well, the first is translation invariance, right? So if I have, let's say, a set X, a singleton X, and I'm adding it to a particular set A, this will be denoted as X plus A, just X plus A for the rest of the stock. So that is translation by a single element. We'll remove the set notation from the element. But the point is, because of translation invariance of the Lebesgue measure, mod of X plus A is just the area of A for all X in Rn and A subset of Rn. So that's translation invariance, which is important because that's why the Lebesgue measure is integral to what we're trying to do. Furthermore, there are ways in which Minkowski addition and translation interact. So that is this particular relation. For all X and AB subsets of Rn, you can kind of move this subset X around. And that's useful because, as we'll see, that counts for something in the proof of the Brunn Minkowski inequality. Finally, there is an interaction between the scaling and the volume, which is very natural to expect. So if X is a subset of Rn and C is a particular scalar, then the volume of Cx is just C to the n times the volume of X. Again, very natural to expect. Finally, the last property, which is very important, is distributivity. Scalar multiplication distributes over Minkowski addition. C of x plus y is Cx plus Cy, where these last two are for all c greater than equal to 0 and xy subset. Right? These properties are useful because they tell us in some sense that we feel in a sort of familiar Rn type setting itself, although we're dealing with sets and set addition and set scalar multiplication. Yes, yes, for all xy subset of Rn. So that matters. Sorry, this mouse cursor is in the middle. Right. So now let me motivate the isoparametric inequality. I mean, there is almost no need to motivate it. We all know that the first thing that we hear when we're small is that when we have objects of a certain size with a certain volume and we try to minimize its perimeter, the first object that comes to mind is the ball. So the ball or a ball, it minimizes perimeter, whatever that means mathematically, when one fixes the volume. And that property is referred to the isoparametric property. The idea that you can have a particular object that when your volume is fixed is very symmetric and easy to understand and yet has this particular minimization property, that is what isoperimetry, that is what captures isoperimetry in some sense. So it's a very natural phenomena to expect, and what we're going to try and do in this talk is mathematically express what it means and prove it, right? So there are many definitions for the quantity that is the perimeter. So this perimeter is involved here, and the perimeter has many different definitions. The one that we will be using is natural because it was defined by Minkowski and Steiner in the 1900s. And not only was it defined by them, but it turns out that it matches in some sense with the so-called Lebesgue measure of the boundary as long as the set is good enough. So our definition of the perimeter is as follows. So if a subset of Rn is a bounded and measurable set, then you define sigma d of A, well, okay, not sigma d, I'll just call it a sigma of A as the following. Well, what you do is you take the Lebesgue measure of A plus epsilon B01 closure. I'll be motivating this, so for now, please bear with me. Well, sorry. So what's happening here is the following. Let's say, I don't know, A is some set like this. What we're doing is, what does the perimeter of A look like? Well, it's the so-called, it's the sides of this triangle in this particular case, right? What happens when I do A plus epsilon ball 01 closure? What set is that, right? What I'm doing is I'm basically adding balls of radius 0 epsilon around each point. That's exactly what I'm doing, right? So for example, in this occasion, what I'm doing is I'm just putting balls of radius 0 epsilon around each point, even on the interior. And so on and so forth. But what does that lead to? What kind of figure does that lead to? What it leads to is something like this. Here's your original triangle, and you kind of get this epsilon thickening around it, right? And you can think of this as a kind of epsilon thickening of the perimeter. You have the perimeter and you've kind of thickened it by epsilon at each point. And what you're doing is this numerator of the perimeter is actually speaking just the area of that particular region, of the region in between A and A plus epsilon B01, this particular region. And we're dividing by epsilon because we expect that as epsilon goes to 0, that thickening goes to 0 at the rate of epsilon, giving us the perimeter. But however, that limit is not expected to exist in general. So what we do is we take the lim instead of the limit. And the reason why that's so important is because there is a result of Minkowski and Steiner. So there is a result of Minkowski and Steiner which states that if you have a convex body K, so if you have a K subset of Rn, which is a convex compact set with a non-empty interior, perhaps that condition is not necessary, but it is certainly true with this condition as well. Then you will notice that this particular quantity, sigma of K, is actually equal to the Hausdorff, the n-1 Hausdorff measure of the boundary of K. And this is exactly what it means, right? For us to think of the measure of the boundary or whatever, right? And one more thing, furthermore, in the case of a convex body, it turns out that the lim inf is actually a true limit in this particular case. So that's another useful thing to know, right? Finally, we can now come to the statement of the isoparametric inequality. And this is actually one definition that we've made of the perimeter, but there are other definitions also available. So for example, the most initial definitions of the perimeter, they involved divergences and all kinds of complicated notations, the likes of D Georgi's definition and so on. But now we can finally state the isoparametric inequality. So the isoparametric inequality, the statement that I'm going to use can be found as in reference R2, that is namely Manjunath's notes. In section 3, it is theorem 2. So it is stated exactly as there. Although Manjunath's definition is slightly different from mine, the statements are exactly the same. And the statement is as follows. If you have a Lebesgue measurable set, which is bounded and Lebesgue measurable set, and you consider a ball that is of the same volume as A. So you let B be a closed ball such that the area of B is equal to the area of A. So you can adjust the radius so that this happens. Then the perimeter of B is actually less than equal to the perimeter of A, which is exactly what isoperimetry is supposed to represent, right? And once again, this is not the most general definition, not the most general isoperimetric inequality available. You can find a more general version, for example, which involves lower Minkowski content and so on. As R6, which is Krantz's book, and it's theorem 7.2.2. So that is a more general version of the isoperimetric inequality, which can be derived as a corollary of what we do, but strictly speaking, it's a much stronger result than the one that we have here, right? Now what we need is okay, so the question is that why have I taken lim inf instead of lim sup? The answer is that in the Minkowski-Steiner version, the lim inf has been taken. And if you read theorem 7.2.22, it involves. It should be, but the most standard version that I know of the isoperimetric inequality, strictly speaking, it involves the lim inf or the so-called lower Minkowski content, right? And the lower, essentially speaking, means you take the lim inf, right? So what we need of this, what we need actually from the isoperimetric inequality is the following corollary, which we will prove, of course. So this is a corollary of the isoperimetric inequality. It's the following. It's basically speaking a statement about the isoperimetric inequality that doesn't involve the ball in any form. So if you have a subset E of Rn that's bounded and measurable, then the following relationship holds between the perimeter and the volume of that particular set. The perimeter is at least greater than equal to some constant involving n times the volume to the power n-1 by n. This particular relation holds for all bounded measurable sets, and you would expect that the ball is the kind of equalizer. It turns out that it's not only the ball which is the equalizer. However, it's not too far from that. that is not very far from the truth. So how do we prove the isoparametric inequality, right? The initial versions of the isoparametric inequality were proved strictly for convex bodies using strictly convex methods. Methods that involved the fact that the volume can be expressed in a very special way for convex sets. For example, such formulas can be found in Schneider's book, for example. Now, what we do is that we present the first proof of the isoparametric inequality that was stated for general sets. And the idea was that it was a corollary of another inequality called the Brunn Minkowski inequality that was also discovered for general sets, which was also again known only for convex bodies, but turns out it worked for general sets thanks to a fantastic trick. So what now I will do is motivate the central topic of this talk, the Brunn Minkowski inequality. So the Brunn Minkowski inequality. Once again, there are many versions of this Brunn Minkowski inequality. As I said, there is one version that is restricted to convex bodies and that has some proofs that are illustrative of convex behavior, if you like. However, in our case, we will give a much more general result followed by a more general proof. Now, how do we motivate the Brunn Minkowski inequality? The Brunn Minkowski inequality is motivated by the fact that not only is the ball isoparametric, but there is another way in which it has a certain optimality. What is that? Well, if you take any two balls of radius r and radius r prime, you take their Minkowski sum and you take it to the power 1 by n, where n is the, you're taking balls in Rn. Then it's in fact equal to the volume of B0R to the power 1 by n plus the volume of B0R prime to the power 1 by n for all r and r prime greater than or equal to 0. So this is an equation that you see here where you see that balls have a certain kind of optimality because this quantity here, this equality, excuse me, that is an aberration. This is an equal to sign here. Now the question is that can we expect the Minkowski sum to interact with respect to this particular function f of x is equal to mod x to the 1 by n, or rather the area of x to the 1 by n. We expect this and the Minkowski sum to interact in a special way. And if we do, then how? The answer to that is given by the so-called generalized Brunn Minkowski theorem. So let me now state the theorem of Brunn Minkowski. I will quickly provide a reference to the theorem that I'm exactly stating from as well. Well, this can be found in reference 1, theorem 4.1. So that's Gardner's survey theorem 4.1. This is the exact version that I'm using. And how does it go? Well, it basically states that f is a concave function. So how would we still rigorously write it? Well, you take a function, you take a lambda between 0 and 1, and you take x, y, bounded measurable sets, or subsets of Rn rather, subsets of Rn, such that, and this is an important condition, I'm going to put this in brackets because this is not obvious. We need to actually assume this. We need to assume the fact that 1 minus lambda x plus lambda y is actually a measurable quantity, is actually a measurable set. So this is not something that is given from the definitions of the Minkowski sum or scaling. This is actually, this needs to be a non-trivial assumption because as it turns out, if you check Manjunath's notes, section 3, you can find sets x and y and a particular lambda such that 1 minus lambda x plus lambda y is not measurable, although x and y are measurable. So this is a non-trivial assumption that is necessary for this talk, that is necessary to state this particular question, this particular theorem. However, once it's stated, then as I mentioned, the concavity of f literally translates to the following statement. So concavity will tell you that this is greater than or equal to the individual sum of the functions. Right?
So take x and y to be convex, then this is okay, right? It will be still.
Yes, if you take x and y as convex sets, then it is true that 1 minus lambda x plus lambda y is convex. It is not. It is in fact true that 1 minus lambda x plus lambda y is convex, let alone measurable. Yeah.
But even if one of them is convex, that is not helpful.
I don't think that is helpful. I am not fully aware, but I don't think that is helpful. I do not believe that is helpful. Right? Now there are two things that we need to, of course, we will start with the proof of the Brunn Minkowski inequality now. However, before proving the Brunn Minkowski inequality, we will prove that there are three statements, three different ways to write the Brunn Minkowski inequality, which are equivalent to each other, but which in fact carry different senses of information regarding this function f. F of x is mod x to the 1 by n. So there is something special about that function. Not only is it concave, of course, concavity has its own consequences, but we will show that those consequences, because of something like the homogeneity of f, are actually equal to each other. So proving three particular statements are actually equal to each other. So before starting the proof, we'll just have a small proposition. And in this proposition, I will leave, I'll just sketch it out. So I will not be proving it in extreme detail. Nevertheless, the proposition is the following. The following are equivalent and all true statements. The first of these is, of course, the Brunn Minkowski inequality as stated above. So the Brunn Minkowski inequality, in brackets, I'll write concavity. The second is the following statement, which looks like a simpler version of Brunn Minkowski, which is that for all x, y bounded measurable such that x plus y is measurable. Actually, wait, this is obvious, so I don't even need to mention this. So if x and y are bounded measurable, then x plus y is also bounded measurable. You can try and prove that as an exercise. Then, in fact, you just get superadditivity. So that is mod of x plus y to the 1 by n is greater than equal to the Lebesgue measure of x to the 1 by n plus the Lebesgue measure of y to the 1. So the way to look at this equation is to think of it as a superadditivity of that particular function. And finally, the third, which is an even weaker notion, is of quasi-concavity. Quasi-concavity will tell you the following. It will tell you that for all lambda xy, as in the assumptions of Brunn Minkowski inequality, you have an apparently weaker statement which turns out to be equivalent. What is that apparently weaker statement? It's the following: 1 minus lambda x plus lambda y whole to the 1 by n. Well, we know it's greater than or equal to the convex combination. That's what concavity says. We will end up doing something even better. We'll say that it's in fact greater than or equal to the minimum of mod x to the 1 by n and the Lebesgue measure of y to the 1. This looks like a strictly weaker statement. 3 looks like a strictly weaker statement than 1. And by the way, this will be titled quasi-concave. So you see here, there are 3 different properties that we've shown of this function f of x is equal to the Lebesgue measure of x to the 1 by n. The first property is the Brunn Minkowski inequality. That is its concavity. The second is that it's superadditive, and the third that it's quasi-concave. Now, actually speaking, for any function, concavity implies superadditivity implies quasi-concavity. So in this case, the fact that they're all equivalent is something interesting. And the proof, which I'll not really sort of elaborate on much, but the proof, the sort of key fact is the fact that f is homogeneous. So f of t times capital X is just cx to the 1 over n, and that's just c times x to the 1 over n, and that's just c f of x. So f is in fact a homogeneous function. And for homogeneous functions, it turns out that quasi-concavity actually implies concavity by itself. So for homogeneous functions, quasi-concavity.
Sarvesh, are you missing any lambda in the third point somewhere? That minimum of, is that
No, actually the lambda is not being missed anywhere. So the question is the following: am I missing a lambda anywhere in the definition of quasi-concavity? The answer is no. I'm actually not missing a lambda anywhere there, because quasi-concavity precisely means that in the middle, all the values that are taken are greater than equal to the values at the endpoints. The values of the endpoints will not involve any lambda, right? They will only involve mod x to the 1 by n and the whatever Lebesgue measure of x to the 1 by n and Lebesgue measure to the y to the 1 by n. So there's no lambda in the right side, and that's exactly what quasi-concavity entails. Is it clear?
okay? Yeah, thanks.
Thank you so much. Right. So for homogeneous functions, quasi-concavity actually implies concavity. That is something that you can check as an abstract exercise. So I understand that we're not dealing with traditional addition here. We're dealing with Minkowski addition and with scaling of sets. However, this kind of a statement can be proved in an extremely abstract setting, and I encourage you all to try it by yourself. But this one line of computation, the fact that f is homogeneous, explains why 1, 2, and 3 are equivalent. And I'll leave the rest as an exercise. But the interesting thing is that I want to kind of come to these three statements, 1, 2, and 3, and quickly give you an idea of why they're also special. Well, the Brunn Minkowski, of course, is concavity of f. That's great. Superadditivity is great because if you think about it, you've gotten rid of the lambdas. There are no more lambdas involved anywhere here. You're just dealing with two sets, x and y to the 1 by n. And all you're saying is that it's a superadditive function. So it's really easy to express. The third, on the other hand, is interesting because if you look at 1 and 2, you can't take x and y non-empty there, for example. The reason why is because let's say you take x as an empty set here. If you take x as an empty set in statement 2, then what you will get is that x plus y is also an empty set. And therefore, if y is something of Lebesgue measure non-zero, then everything falls apart in equation 2. So if you need equation 3, if you need to think of equation 3, the best way to think of it is that it kind of accommodates the situation when x and y can potentially be empty. Because over there, the right-hand side is 0 when one of them has Lebesgue measure 0. So it makes things really easy. Right. So once that is done, what we will do is these versions are all useful to us because they help us think of the Brunn Minkowski in different ways. But we will still provide a proof of Brunn Minkowski inequality as part A. So we will provide, the proof of Brunn Minkowski inequality as written. That is the concavity statement. And the proof, well, it goes where we start with the following observations, right? The first observation that we start with is the following. The first observation that we start with is that if the Lebesgue measure of one of the sets, if the Lebesgue measure of x is 0 or the Lebesgue measure of y is 0, then what happens? Then you see what we have is 1 minus lambda x plus lambda y whole to the 1 by n on one side. And what we have on the other side is 1 minus lambda Lebesgue measure of x to the 1 by n plus lambda Lebesgue measure of y to the 1 by n, right? Or this is one way to think about. Perhaps this is not the best way to think about it. The better way to think about it would be to think about statement B, perhaps. So if you think about statement B, you have Lebesgue measure of x plus y on one side, and you have Lebesgue measure of x on one side and Lebesgue measure of y on the other side, both to the power 1 by n, right? If x is empty, if x has Lebesgue measure 0, for example, without being empty, then one of the terms on the right-hand side is 0. Let's say if mod x is 0, if the Lebesgue measure of x is 0, then on the right-hand side, you're left only with the Lebesgue measure of y to the 1 by n. But on the left-hand side, you'll have some translate of y, possibly by a set of measure 0. But still, it will be something that contains a translate of y. Therefore, it will have as much Lebesgue measure as y itself. So when x or y has Lebesgue measure 0, this statement follows very obviously. Now, what's the second point? what happens when you translate x or y? Well, when you translate x or y, the Brunn Minkowski inequality is retained under translations. And the reason for that is that identity which I told you about, this one, that if you take v plus x plus y, then it's just v plus x plus y. So because of that, what happens is that as you translate, nothing much changes. Your Lebesgue measure doesn't. Lebesgue measures on either side of, for example, equation B wouldn't change if you translate one of the sets. So the Brunn Minkowski inequality is retained under translations. And this is an excellent property because it allows us to use the most beautiful part of this proof, namely the Hadwiger Ohmann cuts, right? So what we will do, how will we prove this? How will we prove the Brunn Minkowski inequality? There will be 4 steps. So there'll be steps, right? Step 1, we will do it for a particular basic kind of set called as a standard closed parallelepiped, which I will define. Think of these as boxes, good, nice boxes whose sides are aligned with the coordinate axis. Which one? Okay, so the question is the following: how does my first observation work? Namely, the fact that if the Lebesgue measure of x is 0 or the Lebesgue measure of y is 0, then the Brunn Minkowski inequality holds. Once again, the answer is as follows. What happens when one of the sets, say x, has Lebesgue measure 0? Then the right-hand side of part B or part 2 of the Brunn Minkowski inequality of the 3 statements that we proved equivalent is just one of the sets, that Lebesgue measure to the power 1 by n. So say, for example, if the Lebesgue measure of x is 0, then the right-hand side is just the Lebesgue measure of y to the power 1 by n. On the other hand, because we're assuming x is non-empty, x plus y at least contains one translate of y. So by monotonicity, the Lebesgue measure of x plus y at least contains a translate of y, and therefore its Lebesgue measure is at least the Lebesgue measure of y. That's the idea, right? Is it clear?
Assumptions you need non-empty, right?
Yes. Yes, I need.
Zero is okay, but
Non-empty is an issue. Non-empty is an issue, except for statement 3 of the Brunn Minkowski inequality, where non-empty is not an issue because the right-hand side is 0. So we will prove it with something called standard closed parallelepipeds, which, as I verbally mentioned, are fairly regular sets. Then we will prove it for, well, disjoint unions of these boxes of the standard closed parallelepipeds. The third is that we can use, these disjoint unions of standard closed parallelepipeds to approximate any kind of set that we need. So for example, while I won't be elaborating on this, typically we use disjoint unions of standard closed parallelepipeds to first go to compact sets, compact bounded sets, and then from compact we use inner regularity to go to any set, any bounded measurable set, right? And 3 and 4 are arguments that I will pretty much be skipping because I will tell you where they can be found. Right. So now let me define, for the purpose of this talk and this talk alone, what a standard closed parallelepiped is. So a definition which is local to this talk is the following. Let's say you have x1, x2 up to, let's say, xn greater than 0, and you also have a vector x in Rn. Then what you can do is you can center a box, or you can have a box, one of whose vertices is x, and such that all the sides of the so-called of a box kind of protrude out of x. So how would that look like? Well, a set of the form x plus a box. So 0, x1 cross 0, x2 cross up to 0, xn will be called as a standard closed parallelepiped. So the choice of words here is as follows. It's a closed set So therefore the word closed. It is shaped like a box, hence the name parallelepiped. And if you look at how it's oriented, its sides are actually perpendicular to the its sides are actually aligned with the coordinate axis. So it's standard in that particular sense. And for the purpose of this talk, I will abbreviate standard closed parallelepipeds both in writing and in speech by SCP. And as you can see, my first proof, the first step, will be to show that for standard closed parallelepipeds, we don't have a problem. The Brunn Minkowski inequality is actually provable. And there's a nice trick for those who are Olympiad enthusiasts. So let me start proving the inequality for standard closed parallelepipeds. And how does this work, right? The way this works is as follows. If you take any two, let's say I'm in R2 perhaps, and what happens when I add two rectangles together? Let's say this is a rectangle 1 or something like that, and here is another rectangle 2. If I take the Minkowski sum of R1 and R2, what I get is just a bigger rectangle, but I also know the dimensions of this bigger rectangle. The width of it, or the height of it in this particular case, will just be the sums of the heights of R1 and R2, while its length will also be the sum of the lengths. So that regularity is nice because it means that we know what both sides of the Brunn-Minkowski inequality explicitly are or should be for this particular case, and therefore we can try to concretely approach or try and prove this situation, right? So what would step 1 say? Step 1 would say the following. So you have two standard closed parallelepipeds. Let's call them X and Y. So X is of the form small x plus 0, x1 up to 0, xn, and Y is of the form Y plus 0, y1 cross up to 0, yn, right? And what do we know here? We know what the areas of X and Y are, of course. Also, note that all the xi's and all the yi's are positive quantities, because if one of them was 0, then we'd be back to a measure 0 situation, in which case we know that we already have an answer. So the area of X is obviously just a product of the small xi, and the same with the area of Y, or the volume, pardon me, of Y, right? By the logic that I mentioned regarding the addition of rectangles, we know that the volume of the set X plus Y is the product of Xi plus Yi, right? And what we need to prove is that, 1 by n, we need to take the power 1 by n, and we need to see if the Brunn-Minkowski inequality works out, right? So how does this work? What we do is we need to show that mod x plus y to the 1 by n is greater than equal to Lebesgue measure of x to the 1 by n plus Lebesgue measure of y to the 1 by n. So what we'll show, it's enough to show that 1 is greater than equal to, we just transpose the Lebesgue measure of x plus y down to the other side. So Lebesgue measure of x by 1 by n plus Lebesgue measure of y to the 1 by n upon Lebesgue measure of x plus y to the 1 by n. Let us write down this right hand side quantity explicitly. What is that quantity? In our case, it is the following. It is the product from I equal to 1 to n, xi by xi plus yi whole to the 1 by n plus product I equal to 1 to n yi by xi plus yi whole to the 1 by n, where what I've done is I've actually distributed the denominator across the two terms. So I have actually written this as Lebesgue measure of x to the 1 by n by Lebesgue measure of x plus y to the 1 by n plus Lebesgue measure of y to the 1 by n upon Lebesgue measure of x plus y to the 1 by n. And then the next line follows as a consequence of that. Now, what can we see about these two terms? The first thing that comes to mind when we see a product of something to the 1 by n, where the product has n terms, is the arithmetic mean geometric mean inequality. And what does that tell you? This guy, both these terms here, are geometric means of some respective quantities. So by the arithmetic mean geometric mean inequality, they are both less than equal to their respective arithmetic means. Observe that all the quantities here are non-negative. So it's obvious that one can apply this inequality. So when we do that, we get 1 by n xi by xi plus yi plus 1 by n summation I equal to 1 to n yi by xi plus 1. But then as written, this quantity is just 1. Because if you take out the xi plus yi's, if you take the summations together, each term is 1 and there are n such terms and you're dividing by n. So this exactly equals 1. And finally, we've shown that for standard closed parallelepipeds, the Brunn Minkowski inequality holds. Now the big question is in step 2, or rather the big insight here is actually in step 2. Yeah. Okay, so the question is, why did I translate small x and small y? Why did I translate big X and big Y by small x and small y? Yeah, perhaps that's not required. That's just there because it's convenient. We know that under translation nothing matters, but we've still put it in for the sake of convenience. Right? And furthermore, in step 2, the way we'll be defining unions of standard closed parallelepipeds, we require the fact that any parallelepiped can be anywhere else. It can be centered anywhere else, right? So that's required. So that's the reason why we've defined SCPs in such generality. Now what we will do in step 2 is the following. We will deal with the situation where X and Y are actually disjoint unions of SCP. So what does that mean? Well, it doesn't mean disjoint in the sort of disjoint union sense. It means the following. You write X and Y in the following way. X as X1 cup X2 up to some XM, and Y as Y1 cup Y2 cup up to some Yn. Okay, I should not use N here. Probably use M1 and M2. Where the Xi's are SCPs, but they are SCPs with disjoint interiors. So we don't say that they should be completely far away from each other. They could probably share a side, but they need to have disjoint interiors. And similarly, the Yi's are also SCPs with disjoint interiors. That's what we insist on, right? Now, what we will do. No, that is not a necessity. So the question is the following. Is there any relationship between the Xi and the Yi? The answer is no. They may freely intersect with each other if necessary. Right. Although later on we will translate and find a certain relationship between them. But at the moment, there is no need to force any such relation on them. Right? Right. Now what we're going to do is the following. How do we work with these unions? Well, we induct on M1 plus M2. That's the first thing that we do. We're going to induct on M1 plus M2. So the idea of our argument is the following. We have X and Y. We will cut X into two parts, which are unions of SCPs, but with smaller number of SCPs involved. And we will apply the inequality to each one and then add them up. That's how it will work. Now, the only question is, how do you cut it? And that's where the Hadwiger Ohmann cut comes into play. So when we're inducting on M1 plus M2, we know that we've already handled the base case. The base case, M1 plus M2 equal to 2, has been handled. Because if M1 is equal to M2 equal to 1, that was step 1. And if either one is equal to 0, then that particular set has Lebesgue measure 0, which has also been handled. So because both of these have been handled, we can now assume that the base case is done, and we can proceed to the so-called induction case. Is done by step 1. So now we come to the induction case. How does this induction case work? Now let's be visual yet again, because visualization is the best way of learning. let's draw X. No, this is X, and this is X1, this is X2, and this is X3, right? Oh, sorry, my handwriting is too small. X3, X2, and X3, right? The question is, so as I said earlier, we're trying to use induction. So what we should do here is try and break this X into two parts such that we can apply induction on either part and then put them together to obtain the Brunn Minkowski inequality for capital X. But how are we going to break it so that we can have induction? Naively trying to do it or assuming that it happens all the time is false. For example, here in red is an example of a wrong cut. So I'm just drawing a line here. As I draw this line, this wrong line, what happens here is that on one side, the so-called downside, you have two boxes that you can see. However, on top, if you notice, you have three boxes because X2 and X3, they are divided into two parts. They have one of their parts, one each is on top, and X1 itself is completely on top. Now, the problem here, and the reason why I can't divide X like this, is because if I'm trying to use induction, X itself was already made of three boxes. So if I'm trying to divide X into two parts, then I should be ensuring that each one has at most two boxes so that I can apply induction, right? So I need a smarter cut. And my smarter cut, if you notice, is located just a little bit above. What I need to do is that line between X2 and X3 and X1, I need to make sure that the cut passes through it. So the black line that you see there, that is a good cut. And why is it a good cut? That cut is good because if you look above it, there's only one box, and that's X1. On top, there's only one box. While on the bottom, you can see two boxes, but that's still less than three. Two boxes. So this cut is a good cut. And the other cut that's given in pink or red is a bad cut. And therefore, the fact that there is always a good cut, always a way in which one can cut a union of SCPs in a sort of convenient way so that one can apply induction, is what is called as a Hadwiger Ohmann cut. So a good cut is called a Hadwiger Ohmann cut. And this bit of intuition by these two mathematicians was basically speaking the reason why one could generalize the Brunn Minkowski inequality to sets other than convex sets. This was the main bit of insight, and this is what allowed induction in some sense. So now we will make the claim. The claim is that there always is a Hadwiger Ohmann cut, but we of course need to be more rigorous. So what is the rigorous statement? The rigorous statement is the following. So we know that X is a union of X1, X2 up to XM1. So the particular quantity that we're concerned with is cutting down on M1. So what we do is we define a cut. So what is a cut? A cut is a hyperplane. So a hyperplane, in this case, it's a coordinate hyperplane. So you can find a particular coordinate, say J, which is less than equal to the number of dimensions n, and you can find a T in R, which is the so-called level of the cut, such that if you consider these two quantities, X prime and X double prime, which are basically the boxes above and below. So that would just be X prime, well, not X prime. It would be X intersection everything above T, everything above T with respect to jth coordinate, and everything below T with respect to the jth coordinate. Well, these are standard, well, not standard close. They are at most m-1 unions of standard closed parallelepipeds with disjoint interiors. This big piece of insight is what sort of underlines everything that happens with respect to the Brunn Minkowski inequality, right? Sorry. Yeah. Somebody asked me to go up, so I'm just showing the claim a little more. Done? Yeah, thank you. So let's prove the existence of a Hadwiger Ohmann cut. How do we prove the existence of a Hadwiger Ohmann cut? Well, the idea is the following. You don't even need to worry about, the fact that there are too many boxes. You just take two of the boxes and analyze the relationship between them, and that will actually be enough to produce a Hadwiger Ohmann cut. Let's see how. Well, in this case, we have, X as the, this almost disjoint union of M1 of these SCPs, right? So we consider the first two of these SCPs, and let's just explicitly label them. So, X plus A1, B1. Well, okay. I mean, it's just included. So I can just say A1, B1 cross A2, B2 cross up to AN, BN. And I can call X2 as P1, Q1 cross P2, Q2 up to P and Q. Right? Now, what I will do is the following. We know that X1 and X2 have disjoint interiors. Now, because they have disjoint interiors, there is a certain direction in which that disjoint interior property is violated, in the sense that their intersections would have measure 0 in that particular coordinate direction. So to assert that formally, you call Ij as the following quantity: Aj, Bj, intersection Pj, Qj. So this is basically speaking trying to capture the amount, trying to capture whether or not X1 and X2 intersect in a certain coordinate direction, right? And the point is that if you consider this set, that is I1 cross I2 cross up to In, this would be a subset of both X1 and X2, and therefore a subset of X1 intersection X2. However, we know that X1 intersection X2 is in a certain coordinate direction. We know that X1 and X2 have disjoint interiors. Therefore, this particular box, at least one of its dimensions, is null in some sense. So, which have disjoint interiors. So because they have disjoint interiors, there is a J such that, well, AJ, BJ intersection PJ, QJ either consists of a single point. So that is IJ is either a single point, or it's just empty. But whether it's a single point or whether it's empty, that implies that there is a certain order amongst the AJ, BJ and the PJ, QJ. So either the PJ, QJ interval is entirely to the left of AJ, BJ, or it's entirely to the right, right? So depending upon that, you can pick your T. So how does this work? It works as follows. So if Pj is less than Bj, then let T be any point in this interval. Or perhaps it could be equal to Pj or Pj. That is also possible. And on the other hand, if Qj is less than equal to Aj, then you let T be in that interval. So Qj. So depending upon which interval is to the left and which is to the right, you put T right in the middle of those two intervals. So think of it as T is in the middle of these two intervals, AJ, BJ, and PJ, QJ. So that is the sort of geometric picture that you should have in your mind when you think of where T is exactly located. So let's draw a diagram again. I'm a fan of diagrams, as you can make out. So perhaps this is X1 and this is X2, right? Let's say this is X1 and this is X2. Let's draw some other boxes just for the sake of it. So this is perhaps X3 Maybe this is x4, maybe this is x5, and so on, right? Now, what would a Hadwiger Ohmann cut look like? Now, what I claim here, I claim that this set, I have a J now. I have found a J and I have found a T. So I claim that Xj, I claim that this J and this T are as desired. So J and T are actually as desired. Let me quickly explain why in a picture. Well, what happens when you apply the Hadwiger Ohmann logic that we just did to x1 and x2? What happens is that you will get something that looks like this. You will get a line that looks like this in this particular occasion, right? So this will be your sort of good cut. Now, what we need to see is not only about x1 and x2. We need to analyze what happens to the rest of the boxes as well, right? So there are two regions here, one to the left and one to the right. Now, what you observe is that x1 is on one side without being on the other side, and x2 is on the other side without being on one side. So what happens to the rest of the boxes? If you look at x3, it's completely to the right. If you look at x4, it's completely to the left, whereas x5 is kind of divided in the middle. But regardless of what happens, each box other than x1 and x2 adds at most one other box to one of the sides. So x3 doesn't contribute anything to the left, but only to the right. X4 doesn't contribute anything to the right, but only to the left, whereas xy contributes one box to each side. But at most one box is contributed on each side regardless of what happens. So the way to think of this is that x1 will belong on one side, x2 will belong on the other side. So for example, one of them could belong to x intersection. Yeah, the bj is less than equal to pj. Sorry. Yeah. So the question was that there was some sign errors that I have made while labeling these boxes. Nevertheless, please keep the geometric picture in mind. That will make sure that you do not get lost in the symbolisms. Right. So once you see this, so x1 is on one side, x2 is on the other side. Now what happens to xj, or I should not use j, j is already being used. Let's say xk, where k is not equal to 1, 2. Well, xk is either completely on one side, completely on the other side, or in the middle. But whatever happens, regardless of the circumstances, it adds at most one SCP to each side. So each xk, k not equal to 1, 2, adds at most one SCP to each side. Right? And because of that, what we've informally proved, but which can be made formal easily, is that the sets x prime and x double prime, which are given by x intersection xj less than equal to t and x intersection xj greater than equal to t, are at most m1 minus 1 unions of standard closed parallelepipeds with disjoint interiors. So this is the so-called Hadwiger Ohmann cut, which is at the center of this fantastic proof that you have just seen, right? And once you have the Hadwiger Ohmann cut, what we need to do is we need to translate. So once we've considered the Hadwiger Ohmann cut, we have now with us this set x prime and this set x double prime, right? Once we have these sets x prime and x double prime, we will translate y so that the relationship between y kind of mirrors the relationship between x prime and x. So how will we do that? So once we've proven the claim, we have a j and we have a t. So given, x prime and x double prime, we will translate y in the direction ej, whether up or down ej, doesn't matter, so that the following relationship holds. If you take y prime and y double prime analogous to, the x definition. So y prime would be y intersection xj less than equal to t, and y double prime would be y intersection xj greater than equal to t. Then you would get the following relationship. The area of y prime over the area of y is equal to the area of x prime over the area of x. No, y is not getting cut. You see x, okay, so the question is the following. Is y getting its own cut? The answer is no. X stays in its place and is cut. Y is just being translated, not so that it's cut, but so that this particular area relation holds. Yes. This hyperplane is the exact same. So the hyperplanes xj less than equal to t and xj greater than equal to t are staying the same, and they are determined by the Hadwiger Ohmann cut for x. But y prime and y double prime are formed by moving y in that direction ej, so that this particular area relationship is formed. And the reason why this area relationship is necessary is because when you're applying Brunn Minkowski, the induction step, this object here, this ratio, which is strictly between 0 and 1, possibly could be 0 or 1, will be lambda. And with this lambda, it turns out that we can apply the induction case. So what we do is as follows. It also note that this y prime and y double prime, they are also unions of SCPs. However, they may be still unions of at most M2 SCPs. So that doesn't change as you translate, right? Because of the same logic that even if it's divided, it's at most one box on each side. So perhaps, but y prime, y double prime could still be unions, M2 union of SCPs, but it doesn't matter because we've managed to reduce M1, and that allows induction, right? So how would induction work? It would work as follows. So you can, so the question is the following. Can you explain why the ratios are equal? X is fixed. X is in a particular position and there's a Hadwiger Ohmann cut. Just try to use the intermediate value theorem, right? Y is somewhere here. Let's say if I move y, if I keep moving it in the direction j, eventually it will kind of, because it's bounded, it will cross j completely if I just absolutely move it extremely to that particular side. So somewhere in the middle, the amount of y that is to the left of that hyperplane is exactly at that same ratio as the amount that x is to the hyperplane. Yes, I'm using the continuity here and the intermediate value theorem. Okay, is this clear? Yes, right. I should mention that. So by the intermediate value theorem. So the reason that this can be done is because of the intermediate value theorem and the continuity of the Lebesgue measure. Right. So y prime and y double prime could still be M2 unions, but it doesn't matter because we've already done the magic with x prime and x double prime. So let's go and apply Brunn Minkowski to x prime and y prime. And what does that give you? Well, x prime is at most M1 minus 1 union of parallel pipettes, and y prime is at most an M2 union. So you've come back to M1 plus M2 minus 1, which means Brunn Minkowski is applicable. But at the end of the day, what does that give you? That gives you the following. Well, x1 plus y1. We'll take the d power, we'll take the n power to the other side. So let's not call it y1, sorry. It's x prime plus y prime. X prime plus y prime is greater than equal to, the individual Lebesgue measures to the power 1 by n whole to the power n. And if you notice, lambda has been defined in such a way, let me show you quickly what lambda is, but lambda has been defined in such a way that this quantity here is actually equal to lambda times the Lebesgue measure of x to the 1 by n plus Lebesgue measure of y to the 1 by n whole to the n. So please observe this. Please observe this. If this is not clear, let me know. But the definition of lambda along with scaling will tell you that this particular statement is true. And what we do is, because we have applied this to the left side, we may as well apply this to the x double primes and y double primes. So for the same reason, you will just get lambda times, well, you won't get a lambda. You will actually get a 1 minus lambda on this particular occasion. 1 minus lambda times the Lebesgue measure of x to the 1 by n plus the Lebesgue measure of y to the 1 by n whole to the n, right? And now you should be able to add these two equations and get what you get. But you need to think about what these two sets are. Now, if you look at what x prime and y prime are, x prime and y prime are x or y respectively intersected with the set xj less than equal to t. Whereas on the other hand, if you look at x double prime and y double prime, they're just x or y intersected with xj greater than equal to t. So now what happens in the sets x prime plus y prime and x double prime plus y double prime? Look at the jth coordinates. Now, if you look at the jth coordinates, if you take any point in x prime plus y prime, its jth coordinate. So if let's say, I don't know, some u belongs to x prime plus y prime, then uj has to be less than or equal to 2t, because that's what the definition tells you. On the other hand, if anything is an x double prime plus y double prime, some v say is an x double prime plus y double prime, then that implies that vj is actually greater than equal to 2t. So x prime plus y prime and x double prime plus y double prime, their intersection must be contained in a set of measure 0, because it's in fact contained in the set of all y such that yj is equal to 2t. And this is a particular thing that has measure 0, which has measure 0. So because of that, because of this particular relationship, what we have is that the area of x plus y is actually just equal to the area of x prime plus y prime plus the area of x double prime plus y double prime. The cross term, the intersection is gone. The intersection has measure 0. So you see, the fact that the intersection has measure 0 means that I can write down this particular equality. And then because of the mini Brunn Minkowskis that I've applied, one was applied with a lambda and the other was obtained with 1 minus lambda, and the same quantity mod of absolute value of x plus, sorry, not absolute value, Lebesgue measure of x to the 1 by n plus Lebesgue measure of y to the 1 by n whole to the n, and the lambdas and the 1 minus lambdas combine to give you a 1, and you just get the Lebesgue measure of x to the 1 by n plus Lebesgue measure of y to the 1 by n whole to the n. Taking the 1 by n to the other side concludes part B of the Brunn Minkowski inequality, which we know is equivalent to part A because of what we've proven earlier. And therefore, we are done with step 2. So we are done now with disjoint unions of SCPs as well. Steps 3 and 4 are standard approximation arguments and may be found in Manjunath's notes on page 32. So for example, as I mentioned, you first use these to approximate compact sets, and then you use compact sets and inner regularity to approximate any bounded measurable set. So steps 3 and 4 will not be covered by me. They are extremely standard arguments, and I will leave them. So the idea of this talk so far, how much? I have 5 minutes left, right? I have 5 minutes left, right? So in the remaining 5 minutes, I will quickly try and prove the well, I need to prove something called the Minkowski's first inequality. So I will prove the Minkowski's first inequality, and then tomorrow or the next session, I'll quickly prove that the Minkowski's first inequality implies the isoparametric inequality. So what is Minkowski's first inequality? It's basically an inequality that says the following. If instead of looking at the perimeter, which comes from adding balls of radius epsilon around each point and letting epsilon go to 0, if I don't add a ball, but I instead add some other object, some other Lebesgue measurable set, then what relationship can I expect between the volume of the thickenings and the individual volumes of the two sets involved? So Minkowski's first inequality states the following. Again, Minkowski's first inequality was stated for convex sets, but it turns out that it is generalizable to our situation. So it states the following. So you define this particular quantity, which you can think of as a kind of modification of the perimeter, define for bounded measurable K and L subset of Rn the following quantity. You have sigma of K comma L is 1 by n, limit epsilon tends to 0. So this 1 by n is just a formality really. Perhaps it is not really required, but because it is part of standard definitions, I include it. So you take the lim sup as epsilon tends to 0, but this time you are translating by L. So instead of covering every point around K by a ball, you're covering it by whatever L is, right? And if you define, sigma KL like this, then it turns out that sigma of KL is actually greater than equal to the volume of K to the n minus 1 by n times the volume of L to the 1 by n. So this particular relation is very interesting. And how do we prove this? Well, as usual, when we prove this, we will first cut out everything of measure 0. So if either K or L has measure 0, then you can check that this inequality is obvious, because the right hand side is 0, whereas the left hand side has to be some particular non-negative quantity. So then this is clear. So we will assume from now, without loss of generality, that both K and L have measure non-zero. Right. Once we do that, let us look back at this definition of sigma KL and let us take the n in the sigma KL to the other side. So write n sigma of K comma L as the lim as epsilon tends to 0 of the area of K plus epsilon L minus the area of K by epsilon. What we're going to do here is that we're going to perform a re-indexing. We will let a particular variable t be such that t by 1 minus t is equal to epsilon. This re-indexing is done in such a manner that if epsilon goes to 0, then t also goes to 0. Once it's done in that way, the advantage of this is that you can apply Brunn Minkowski with this t, whereas you couldn't do it with the original epsilon. But once you substitute it, you get the following. That n sigma of K comma L is the lim as t tends to 0 of K plus t 1 minus t inverse K, rather L, excuse me, minus the area of K by epsilon. Oh, sorry, I've replaced epsilon as well. Yeah, t is coming to 0 from top. T tends to 0 plus. Because epsilon is coming to 0 from the top as well. So t will also come to 0 from the top. That's important. Yeah, right. I didn't feel that there was a necessity to mention it, but now after being pressed, I will do so. So what we will do is we'll find an alternate expression for this mixed perimeter, the sigma KL. And how will we do it? We will actually multiply top and bottom on this particular occasion by this quantity 1 minus t to the n. So when we do that, what do we get? We get again lim as t tends to 0 plus of, this time by homogeneity, we will be able to absorb the 1 minus t inside. But for the k, we will not absorb it. It turns out that we are going to perform a limit argument, and therefore we will not absorb the 1 minus t to the n inside the k, and we get t times 1 minus t to the n minus 1 on the bottom. Now, as t goes to 0, 1 minus t to the n minus 1 goes to 1. So we may as well ignore this term. This term here, this 1 minus t to the n minus 1, this just goes to 1. So we will ignore this. This need not even be part of the conversation anymore. But once you do that, what we will do is we will add and subtract a particular quantity that will allow us to isolate this 1 minus t to the n. And what do we add and subtract? We actually add and subtract mod k by t. So t tends to 0 plus. Now what we write will break into two terms. Mod of 1 minus t k plus tl minus the Lebesgue measure of k, plus on the other side you will get 1 minus of 1 minus t to the n by t times the Lebesgue measure of k. This is what you will get, right? And if you look at the second term here, the second term here actually has a limit as t tends to 0. And what is that limit? That limit is just n times the volume of k. So this individual thing here, that goes to n, and then multiplied by the volume of k, you just get n times the volume of k as t tends to 0. So therefore, what we have done is we have obtained expression for the for sigma kl, and the expression looks as follows. It looks as n sigma of k comma l is equal to limit inf as t tends to 0 plus of the area of 1 minus tk plus tl minus the area of k by t plus n times the area of k. So this formula is nice. This is a different way of writing this kind of volume. Okay. Yeah. I'll be wrapping up in 3 minutes. So once this particular identity is proved, then you see what we have. If you want to go back to, for example, f of x is equal to the volume of x to the 1 by n. If you look at the first lim_inf here, it's actually the lim_inf of fn f of something to the power n minus f of x to the power n, f of k to the power n divided by t. So there has to be some relationship that's going on there, right? And the answer is the following. You just make a very simple manipulation. So how do you do it? You make the following manipulation. The limit infimum as t tends to 0 plus of, well, let's say f of t, or rather actually f has to be defined a bit more carefully here. If I define, say, excuse me, if I define, say, f of t as the volume of 1 minus tk plus tl whole to the 1 by n, then what I'm trying to estimate here is the following: f of t minus f of 0 by t, right? If I try to estimate this particular quantity, I'll write it in the following way. I'll write it as limit infimum as t tends to 0 plus of f of t to the power n minus f of 0 to the power n by t times, I just multiplied by something, so I'm just going to go out and divide by it, right? So I just get f of t to the n minus f of 0 to the n by f of t minus f of 0. So writing it in this way is convenient because, again, as t goes to 0, if you look at this second term, because of what we know about this particular ratio and about differential quotients, this goes to a very convenient quantity. It will just go to 1 by n mod k to the n minus 1 by n as t goes to 0. And in fact, this is a limit. So yet again, you can take this out. But furthermore, we also know what the lim_inf is, because the lim_inf is also given by this particular mixed formula. So this lim_inf that we have written on the left side is actually equal to the following quantity. It's equal to n sigma of k comma l minus n volume of k divided by n volume of k to the n minus 1 by n. And what do we know about this left-hand quantity by the Brunn Minkowski inequality? This quantity, lim inf of ft minus f0 by t, this is definitely less than equal to f of 1 minus f of 0, because that's just how concave functions work. Concave functions have a reducing slope property. So if I draw a concave function like this, then if I take its slopes, as I go to the right, as I move further and further to the right, the slopes decrease. So the slopes decrease as I go further and further to the right. So what's happening here is that f of t minus f of 0 by t is like the right hand derivative as you go towards 0, whereas f of 1 minus f of 0 is formally f of 1 minus f of 0 divided by 1 and is therefore a particular slope that because of concavity, excuse me, is going to be smaller than, I reversed the sign by mistake, it's going to be smaller than this particular limit. But we know what f of 1 minus f of 0 by 1 is, because we know what f is. So f of 1 minus f of 0 by definition of f as written on top here is just the area of L to the 1 by n minus the area of k to the 1 by n. So the conclusion of what we've written, so this is by Brunn Minkowski and concavity. So the conclusion, or what we have so far, is that n sigma of KL minus n volume of k by n volume of k to the n minus 1 by n is greater than equal to the area of L to the 1 by n minus the area of k to the 1 by n. And now you can rearrange and complete the proof. Please rearrange and complete the proof of Minkowski's first inequality. So this completes my talk for today. In my next session, I have the following things to cover. I will definitely need to prove the isoparametric inequality, first of all, as stated, in this lecture. And then I will show some functional corollaries, or rather functional consequences of the isoparametric inequality, such as the Sobolev inequality and the Gagliardo-Nirenberg inequality. And finally, there is also a need to discuss the equality cases of the Brunn-Minkowski inequality. So a discussion on that may also ensue in the next talk. Any questions? Yes. No, the only way, so the question is there any physical interpretation of the mixed perimeter? Okay, I cannot answer this question. Sorry, I'm not aware. I will say that to the best of my knowledge, I do not know of any such conditions. Because yes, if L is a ball, then there is a natural way to think of it. However, if L is anything else, then it could just be an arbitrary looking sort of thickening. So there is no reason to expect, apart from the just the pasting logic, what this has to do with anything. But yeah. Any questions? Okay. Thank you very much. Thank you very much for attending my talk, and looking forward.
Yeah, thanks, Sarvesh. It was very clear. Thank you.
Yeah, thank you very much.
Yeah, maybe we should thank the speaker. Yeah.
Thank you. Wow. Thank you so much. Thank you so much. Really, thank you so much.
So you'll make the lecture.
These notes will be made available. I'll make sure that by today I, correct my handwriting somewhere. It's horrible. So I'll just clear my handwriting up a little bit, edit this, and by the end of tonight, hopefully it will be nice. Yes, this will be probably converted to PDF and posted.
Given the link, but just that sometimes PDF is more.
Yes, this will be converted to PDF and posted. Thank you so much. Thank you so much. Yeah, please. Thank you. I now need to work hard.
Specific lecture notes.